Well, good morning. Good on you for those of you who made it for this broadcast. I know things are getting pretty crazy up in that part of the world right now. So I'm glad you were all able to be here. If you're watching on the video later, I hope um, that your situation is under control and everyone's doing okay. Morning, Glazer. Good morning, Tyler. Good morning, Captain Price. Morning to everybody who's watching. So we'll take our minds off other things for a while here. I know I don't have the most exciting menu of offerings, but I hope that you'll agree with me that it's pretty neat to sort of have the sense that you have your fingers sort of down inside of the processor in this class. It's one of the things I enjoy about it. Is that we strip away some of the layers of programming language and actually can manipulate hardware directly on the processor in a sense. So I always sort of like the activity, and hopefully if you're watching now or you're watching later that this will give you something else to put your mind to for a while if you're stressed about what's going on. For those of you who don't know, the campus is closed if that was part of your plans today. If you're doing one of the classes that was meeting live, no doubt you're going to hear from your instructor that you'll be doing class online for a bit. I don't know how long that is, but anyway, just to let you know, make sure you're checking your communications from Butte College and your teachers so that you know what's happening. In terms of my class, we're not going to change anything. We'll just keep going. I'll do my live broadcast. This week, of course, I'm doing it today because Monday was Labor Day and I would get in trouble if I had worked if I had asked you to show up to a class on Labor Day. And then we'll be back to our normal schedule and I will put up the videos and all those things. Okay, so today we're finally actually going to get to touch the processor through our HLA code a little bit, which is always fun. Let me start by I'll stop doing this eventually, but just to make sure that everyone has seen this several times. I'm on the home page in Canvas for our course. I messed up, so apologies to you if that caught you out. I put this announcement on the wrong class, and then I didn't fix the announcement for your class until early Monday morning, but this top announcement here is because we're doing the lecture now, the broadcast now as opposed to Monday because of Labor Day. And then if you've been watching the videos or been coming to the broadcast, you know that originally I had planned to do a team project, but I've dropped that entirely from the semester. It won't appear at all because we have plenty of other work to do, and I just didn't think there was a good place to fit that in. So those aren't really new things, but that's the announcements. For your class, I am about finished with week 11 content. So for those of you who hope to work ahead or like to work ahead or at least like to look ahead, you should see week 11's material appear sometime later today. So in the next several days, I'm going to try to finish all of your content so that you have the option, if you want to, of working ahead on several things. Right now, everything through week 10, including the first individual project, everything through week 10 is available. And also project 2 is now available if you want to have a peek at that, but that's way in the future. So that's all I got for newer stuff. So I'm going to go to the modules page, which you could also access from the home page. We're in week 3. So just step through the pages and just sort of as a reiterating the course orientation. So our goals for this week is to get a handle on what a register is, and more specifically what the registers on Intel processors look like. If you are into computer hardware, then you may be wondering about the x86 part and how this maps into modern processors. So in our class, we are doing 32-bit Intel processor work. So your computers pretty much all of you, it will be true, are 64-bit Intel processors, most of you. But we're doing a slightly older school of Intel processor, the 32-bit, or what we call x86 processor family. There's no reason to not do 64-bit as opposed to doing 32-bit. All it really means is that the values are smaller. And for a class like this, the goal isn't to make you a proficient assembly language programmer. It's to give you some sense of what's going on inside of that processor when I write a for loop, as an example. So anyway, x86, that means we're doing 32-bit Intel processors. And 32 bits, this doesn't come up for several more weeks. But what we're really talking about when we say 32 bits is how much memory we can address, how much memory we can gain access to and have addresses for. 64-bit processors can address a much larger amount of memory than 32-bit processors. That's all that really means. Okay, so registers, the concept of register overlay, which is just kind of cool, I think. We'll talk briefly about the eFlags register, and then we'll keep practicing with numbering systems, binary, decimal, and hexadecimal. And then write a program that allows us to explore registers and sort of look at data using these numbering systems, at least hex and decimal. All right, that's the goals for the week, and that was a lot of talking around that. Registers. Continue the numbering systems and then add to what we know about how to write HLA programs. The HLA programming in this class is mostly so that we can sort of feel the concepts in software. So we talk about registers. Now let's go write a program where we actually use the registers to do stuff. That's what that's about. Okay, so the readings. I added a Wikipedia article in here, and I'll just remind you, when I have a Wikipedia article, usually you're going to find what you need for the homework questions in the first paragraph or two at the top of the Wikipedia article. I try to remember to put this note in here because most of the time you don't need to read all the way down these entire Wikipedia articles, just enough to get a definition out of it. So I wasn't happy with the way our Art of Assembly book defines register, and I was happier with the way Wikipedia did it, so that you come away having a good sense of what we mean when we say a register on a processor. And then you've already been reading in chapters 2 and 3, so probably you're starting at this point, week 3, to get a sense of your power to read selectively. So if you look at the assignments and you see the questions and you see what the lab's asking you, you can start to sort of dive down into these chapters to pick out specifically what you want. And then I've also linked into our programming languages standard libraries, specifically the input handling part of the standard library. So in an HLA program, if we want someone to type something at the keyboard, how do we do that? And that's included in the HLA standard libraries. And then I'll remind you that when we're done, I do my moving video around and getting it submitted for captioning. And then later today, I will post or embed the lecture that I'm doing right now inside of this page. And there's a checkbox on the page when I do the embedding that allows me to notify everybody I did that. So I'll start clicking that checkbox so that you'll know when the video lands on the page. Okay. The homework, that's for you. So as always, I've made changes. Okay, I don't know what I did, but I'll save it and hopefully not break something. Anyway, the homework, that's for you. That's so you go do the readings, and there's 10 homework questions that highlight the things that I think were most important for us to take away from this week's experiences. The lab, that's where we're going to focus my efforts today here on the broadcast. So I'm going to try to give you a really strong start on the lab. It looks like a lot, but it's very repetitive. So once you sort of work out one section of it, the other sections seem pretty easy, if repetitive. But sometimes for some of us, repetition in our learning can be helpful. And then there's a little set of sort of tips at the top. So we're going to come back and do the lab. I'm not going to do all of it, but I'm going to do a fair amount of it, so that when you sit down to work on it for yourself, hopefully you'll just be able to continue from where I left off and not find it to be any problem. Okay, so it looks like a lot, but it actually is just one thing repeated 3 times in slightly different ways. So I'm going to go ahead and finish clicking through the weekly content just to look at it all, and then I'll come back to the lab. Okay, so as always, there's Piazza discussion. This week is trying to get you all to sort of help each other navigate the HLA standard libraries a little bit. So you go read the documentation, and then sort of write tips and tricks for each other, like how did you figure out how to read in an integer, that kind of stuff. And then the last page is the reminders. So I have the same setup every week. The reminders is just to gut check yourself before you call it the end of your week for this class, that you submitted the homework if you're going to do that you submitted the lab if you're going to do that you posted in Piazza to join in the discussion, and then the things that are in your future. So this individual project 1, it's available, and probably next week I'll take a brief look at some of the things to consider when you start working on the first HLA programming project. Okay, that's all of that is by way of sort of getting us set up to look more carefully at the lab with a little bit of old school picture drawing to set up for that. So let me switch my setup here. Take the browser down, put the camera up. So I know I don't have the best setup in the world, but hopefully it's adequate to make a point. So what I've got here is basically a motherboard. They're a pretty cool company, but it's a miniature motherboard. And the reason why I have this is because I don't want to take a computer apart to show you a picture of a processor. So I have this miniature motherboard. You can see it fits in the palm of my hand. Because I wanted to just get us oriented mentally to what it is that we're about to do with our software. So this square right here, if I can get the pointer recorded, that's the processor on this motherboard. So on the motherboard on your computer, somewhere in your computer is a board like this that has stuff wired to it. And somewhere in there also is your computer's processor. For most of you, your computer is going to have some kind of Intel-based processor. This processor actually on this little miniature motherboard is called a RISC-V processor. It's a different architecture. But again, I'm just using it for the picture of it. Yeah. Can I get it? There it comes. So the reason I'm showing you this picture is because when we talk about registers, we are talking about memory that's actually built into the processor itself. So when we write a piece of code that accesses a register, it's way, way, way down in the processor, a little tiny memory bank, where we can place all kinds of different data inside of it. And that's going to be true when we write HLA software as well. We're going to use the registers, which are little memory cells right in the processor itself. The reason why registers are good is because they are fast. Because it is memory on the processor, that's as fast as we can possibly make it for the processor to access the data that it needs. If we were to, for example, I'm kind of faking it here, but let's say this is RAM. Now that's pretty close physically, but if I were to create variables, they would be living in a separate module, and to access them, the processor would actually have to go out, find them in RAM, get the data, and then bring it over to the processor. So the reason why we like registers is because they are as fast as it can possibly be to work with data in a processor. So in x86, the question is how big are the registers? So in x86, we're going to be using 32-bit registers. On your desktop, you actually have 64-bit, and I'm going to show you how that works actually, because it's kind of cool the way that your computer can actually support 32-bit assembly programming, even though your processors are 64-bit. On this board, I think they're 64-bit. I think the registers on this board are 64 bits. This little miniature board, by the way, is called a Hi-5. It's designed for making sort of embedded circuits, like control systems on vehicles and stuff like that. I like doing this kind of programming. So anyway, just so you sort of have a mental picture, you would never be able to see a register. They're so tiny, but they're in the processor. And the advantage of them is that they are very, very fast, the fastest way that we can have to get data into the processor. Every time we store something on a hard disk or create a variable in RAM, that actually slows down the processor for accessing the data. Okay, so there's that thing. So now let's just draw a picture of processors, the processor registers. So I'm using the word register here. Okay, so there's another question about, is a register the registry? And the answer is no. So in Windows, the registry is actually a data structure where the operating system keeps information about configuration options and software installations and other things. So the registry is more like a database that is stored inside of your computer, whereas the register is actually the circuitry on the processor itself. So sorry I missed that question, but it's a good question. Okay, so a register. So you have to remember, when I draw this picture, that this is inside of that tiny little processor chip, somewhere way down in there. I'm just sort of drawing a picture so we can have a mental image of it, is a little memory bank. So one of the registers on Intel is named EAX. The register names are defined by Intel. So if you're on an Intel processor, it's going to have an EAX register on it. So that's effectively a built-in variable that always uses that name, EAX. That's how you code for that register, and you cannot change the name of it. It is sort of hardwired into the processors that there is a register on an Intel processor that is named EAX. EAX is 32 bits. So you get 32 bits of storage in there, which would allow you to store anything that's 32 bits or smaller. Can be stored in there. Okay, and let's deal with EAX first, and then we'll look at the others. So there's several of these. We only actually ever use about 4 of them in this class, but there are more on there than just the 4 that we will use. But this is one of them, EAX. One of the cool things about this, though, is that EAX is actually laying over the top of I wrote that way too small, didn't I? Let's see, I just moved the camera closer if that addresses my problem. So AX, this EAX actually lays over the top of a smaller register called AX, which is 16 bits. So whenever I store data in EAX, I'm actually also kind of laying data over the top of and into AX by its nature. So EAX is 32 bits. AX is actually the 16 bits that are on the sort of lower right hand, we call the low end of EAX. These low 16 bits actually have their own name called AX. So these are basically one and the same memory bank, but if I reference EAX, I'm talking about all 32 at once. If I reference AX, I'm only talking about these 16. So you kind of have to, again, build a mental picture in your head. If I put data in AX, I'm also putting data in EAX because AX is a part of EAX. And if I put data in EAX, I'm also putting data onto AX because it is that lower half. There's two more, actually. There's AH and AL. So AH and AL are really just two halves of AX with their own distinct name. So when I talk about AL, I'm talking about 8 bits. These are 8 bits. So when I say AL, I'm talking about a specific 8 bits, which happens to be the sort of low-end 8 bits of AX and is also, by extension, then the low end of EAX. So I hope that this makes some kind of sense. We call this register overlay because EAX overlays AX, which overlays AH and AL. The H means high and the L means low, so these are the high 8 bits of AX and the low 8 bits of AX. And then AX is the low 16 bits of EAX. This half up here, by the way, the 16 bits up here, they don't have their own name. They just don't. That's just the way that it is. You can get to them, but they don't have a distinct name. So if I'm talking about AH, I'm talking about a set of 8 bits right here that are by themselves have the name AH, but they're also the upper 8 bits of AX, and then they're also sort of this little segment of EAX 8 bits. So if you touch any of these registers, you are usually touching all of the rest of them at the same time. The only one that you can touch without touching another is AL and AH because they don't interconnect in any way. That's correct. So the question is, if I put data in EAX, does that affect AX as well? And yes, it does. It also, because of that, because EAX affects AX, it also affects AH and AL. I'm going to drum up an example so we can look at this. Now, if you're on a modern computer, I'm going to draw my camera out a little bit. If you're on a modern computer, the way that they made 64-bit computers is they added 32 more bits up at the top, and they called this whole thing RAX. So on a 64-bit machine, like most of you have at home, if we were doing 64-bit programming, we would also have access to RAX, which is all 64. EAX is the lower 32 of RAX. You see how all those things kind of overlay each other, which is clever engineering, I would argue. The cool thing about Intel's processor design is that because they keep doing this overlay thing, it means that usually your software is backward compatible, or the processor is. So if I have old software that was written in the 16-bit days, it's still going to run on an Intel processor, and that's pretty dang neat. Okay, so that concept is called register overlay, and we're going to do some software experiments so that we can actually see that in action. Okay, one other concept before we go into the programming. It's not really a concept, it's just, I guess it's a concept. I'll stick with calling it a concept. Okay. The idea of a general purpose register. So there are a lot of registers on our x86 processor. Some of them have predetermined purposes, and you're not supposed to program with them. Some registers are called general purpose registers, and what that means is that you as a programmer are allowed to use them for whatever you'd like. The ones that we're going to focus on in our programming are these. So you're going to see these a lot this semester because these are going to be our go-to general purpose registers. And again, a register is a memory cell on the processor itself. But general purpose, it means that there is no prohibition against me just using them in my programming for whatever I want. That's what the general purpose part means. And then while we're here, let's go ahead and do yeah, I think that must be true. Compatibility mode in Windows has to rely upon the fact that Intel, its processors are almost always backward compatible. That's a good point. This is connected to compatibility mode if you've ever used it in a Windows system. Okay, so these four, and these four have the same overlay scheme. So EAX, the 32-bit general purpose register, overlays AX, that's its lower 16 bits. EBX overlays BX as its lower 16 bits. And then you can guess where this is going. So ECX, its lower 16, is called no, so the question is if I have an AMD processor, is it emulating? And no, AMD actually uses Intel's designs. So AMD actually manufactures Intel processors. They take Intel's designs on paper and they produce processors using the same design. What's in it for Intel, by the way, is that AMD has to pay Intel money for the design work that Intel did, and then they turn the designs into manufactured processors. Intel, of course, also manufactures processors. There are companies in the world, by the way, that design processors and sell the designs but don't actually manufacture them. AMD does have some of its own designs, but most of the time when your machine says it has an AMD processor in it, it's an Intel processor design manufactured by AMD. Yeah, PowerPC is a completely different processor architecture, so the register set's going to be different. The instructions are going to be different in places, so those would not be compatible like in the same way. We're just talking about compatibility between newer Intel designs and older Intel designs. Okay, so ECX overlays CX as its lower 16. EDX overlays DX as its lower 16, so you see the pattern. AX can be broken into two by name, AH and AL, and it's the same for all of the rest of them. BH, BL, CH, CL, DH, DL. So you have a whole bunch of different ways of accessing processor registers depending on how much data it is that you need to be storing. But I just want you to notice there's a pattern here. So EAX overlays AX, which is the lower 16. AX overlays AH and AL. H is the higher 8 of the lower of this 16, and AL is the lower 8 of this 16. And then remember that by extension, AL is also inside of AX, because these are all really the same processor. This is just names for different portions of it. I'm going to clear my throat. Hold on, I'm going to cut the volume for that. Okay, sorry. Okay, so there's my little sort of crude pictures. Now let's see what it feels like to do this with a little bit of software. All right, so here's my, I was just going to walk through this part, so I already started up my Ubuntu, PASSWORD, and then press enter to log in. And then I'll go through the same routine, so get inside the CSCI 10 folder, use the tool menu to open a terminal here, and confirm that I'm in the right location so that the commands are all easy to execute. And then I'm going to fire up a text editor. And then from here, I'm going to save this. And this is a part to be careful of. This may have bit you before. But when you save your document, make sure that you get it inside of the CSCI 10 folder, or you'll have to do some other steps. So just make sure that when you're saving it, that the initial save goes into the CSCI 10 folder, and that you name it with no spaces. So for us, this will be lab 3, and with .hla as its extension. So check all those things until you've got good habits. I can also see that I'm in the right place because all of my other HLA stuff is here, but I'm on the user's desktop CSCI 10 ASM folder. And then I chose the name lab 3 no spaces .hla. And then I'm going to save that. Okay, so why is the HLA syntax highlighting not working? Oh, now it is. Okay, never mind. I don't know what I was thinking. Yeah, I needed to save. That is, in fact, what it was. I just hadn't saved. So I'm just putting a reminder. I'm not going to put documentation because that just fills the screen. And we'd rather be focusing on the examples I'm going to show you. So let's just start with a couple of simple examples so you get a sense of why the lab is this week what it is. So program, this is the way I like to name things. It's just, I think it looks nice, so that's what I do. Just remember that HLA has the same naming rules as most other programming languages do. I know I'm going to have an include for the standard library. Yeah, I guess that explains it. It made me save it. Even though I put .hla, it made me do an initial save before it actually switched over to HLA mode. 3. So I know this feels a little different, HLA, because it doesn't have the curly braces, and it has extra words like if, then, end if, and that kind of thing. So you'll get in a habit. Just be on the lookout for that kind of stuff, because in HLA, when you start something, like eventually we'll do procedures, or if you open up an if statement, or if you open up a for loop, or you open up a program, those things in HLA all need some kind of closing or ending. So here's the ending of the program that was begun here. Just, you'll develop an eye for it. Okay, so I'm going to do some actual binary, and I'm just going to do this so that it's sort of very, very, very obvious, hopefully, what's going on. So I'm actually going to load a binary value. So you can code in binary directly in HLA. And I'm going to start by doing this. 1, 2, 3, 4. In HLA, every 4 bits is a nibble, and it's a lot easier to read to put underscores in there, and it's allowed. So that's 4, 5, 6, 7, oops. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 26, 27, 28, 29, 30, 31, 32. That's a 32-bit binary value. And one thing, I'll probably keep saying one thing. There are many things that you're just going to have to develop some memory for. Like if you open a loop in HLA, there needs to be something that closes it since it doesn't use curly braces. But another thing that we'll add to the mix today is that the sizes of things have to match. So I think this is really good training for a programmer to get accustomed to the idea that if I'm doing 32 bits of data, the destination for that data needs to be 32 bits. So the sizes of things need to match. So I'm going to do something wrong here. Now I would get, in fact I will get a compiler error if I run this, I suspect. But I'm not going to waste our time with that. I'm just going to sort of stop and ask ourselves, what is wrong with moving a 32-bit binary value into AL? Good one, Captain Price. So AL is 8 bits. You cannot move 32 bits of data into 8 bits of register. They don't match. It won't fit. So can I use a H? No again. And the answer again is because AH is also an 8-bit segment of that bigger register. Good one. You're exactly right. AX. Okay, I'll answer that. Let me get an answer on the AX. So AX is 16 bits, so you can't put... So the reason why this is 32 bits is because there's 32 binary digits here. There are little groups of 4. That's 4 bits, 8 bits, 12 bits, 16 bits, 20 bits, 24 bits, 28 bits, 32 bits in sum. So that's a 32. Now they're all zeros right now, so it's just a fancy looking 0 basically. All right, so EAX is the correct choice here because if I want to move 32 bits of data, I need a 32-bit destination to put it there. Now I could also have used EBX because it's 32 bits as well, so that's fine. I could use ECX because that's also 32 bits, so the sizes match, and I could use EDX because it's also 32 bits, and because the sizes match, that's all allowed. Okay, so there's that. The sizes have to match. You're going to see errors that'll say things about the sizes not matching, and that means that you tried to do 2 different sizes of things in the same instruction. Yeah, good one, Tyler. That was EAX. Let's try it. So the question is, if I try to use AX, am I going to get a compiler error or will it truncate? My fingers crossed, I should get a compiler error because that's not a good thing. But let's see if it complains. No, it did, in fact, truncate that. So in the case of this literal data, it just dropped the extra zeros. But get in the habit of matching the sizes because there are places where it's not going to do it. Okay, so EAX. So now what I want to do is do, let's actually put all ones down here. Okay, so the reason why I'm doing this sort of, yeah, the HLA compiler tolerated it, but it won't in every case do that. So just be in the habit of matching the sizes of things. So the reason why I've set it up with all this binary is to get you thinking the right way about how these registers work. So this is perfectly legal. The question is, if I load up all ones in this lowest 8 bits, besides EAX, what other registers are going to be affected? Close. Captain Price is very, very close. AL, that's the lower 8, so that's true. It's getting changed. The next 8 up from there is AH. So not AH. So yes, AL's true. That's the lowest 8. AH is this 8. So those are not being affected. And then one other. And Captain Price already had it in there, but AH will not be affected because those are all zeros. AL will be affected. Those are all 1. That's true. EAX is changing because it covers all of them. So all of EAX is affected. AL is affected. AH is not. And then one other. That's good. That's yeah, AX. So all of this 16 is the AX portion. So the idea here is that you have to try to picture that EAX is sort of covering over the other 3. So that lower 16, it represents AX, and there are parts of AX that are being changed. Pretty freaky. Which means, by the way, so if I were to print out, let me set something up for this. So as a reference, let's convert this into hexadecimal. And then I'm going to convert it into decimal. So if you haven't practiced this, it's a thing to practice. Oh, let me show you a trick. If you go down here, hopefully it's true. Let's see. I'm searching on my Ubuntu. Let's see if there's a calculator installed on here somewhere. I sure would like to have a calculator. Here's a KCalc. I'm going to try that. Let's see if it works. So Captain Price says, yeah, 3 registers. That's correct. So EAX is being affected, AX is being affected, and AL by those ones. If you go to accessories here on your Ubuntu, there's a KCalc, and let's see if it does it. Pro tip here. Yeah. Does it have a programmer mode? It has a science mode and a numerical system mode. So anyway, if you launch this KCalc and you go to the settings, you change it to numerical system, you'll find that you can actually have the calculator think in binary, hexadecimal, decimal, binary, and octal, even though we're not going to use octal. You can switch between the different numbering systems inside of the this editor. Now I also want to see, can I show, okay, show bit edit. So this is the other thing you want to do. Super helpful. Windows calculator will do this as well, by the way. So I changed the settings to numerical system mode, and I'm going to show bit edit here. Now this is showing bits for a 64-bit machine. We're only interested in the bottom row, which is the first 32. But I'm going to actually I'm going to change this to hex, and I'm going to tick off these lower 8 that I did on the screen. 4, 5, 6, 7, 8. So in hexadecimal, this looks like FF. And if you haven't done practice with this calculator can help a lot. So what I want to do is translate this binary into hexadecimal first. The first two nibbles, so all ones translates into an F. And this all ones translates into an F. And then what you would do technically is you take all zeros. There's 1, 2, 3, 4, 5, 6 more nibbles of all zeros. 1, 2, 3, 4, 5, 6. Technically, this is the hexadecimal rendering of this binary value. You go a nibble at a time, so that nibble becomes the first 0. This nibble becomes the second 0, third 0, fourth 0, fifth 0, sixth 0, F, and then F. Now the other thing I can do, though, in this calculator is I can switch to decimal mode, and I can see what this same binary sequence looks like in decimal. It's 255. Pretty sweet. Okay, so I did that all so that you kind of understand what's about to happen next. So these numbers right here represent 255. So if I output them, and I'm going to output them with AL. So I'm literally just going to reference those lower 8 bits and output them. And let's see what it looks like. There is a reason why it's negative, although it shouldn't look like that unless we use the... So AL equals FF, that's what I expected. AL is just these parts. Now if I print out AH here, I wish it would have kept that indent for me. If I print out AH, that's going to be these 8 bits, and it should look like 0. And that's what I expected. It did. So someone noticed that it's printing out hexadecimal. So in HLA, if you do an output on a register, by default it prints in hex. Isn't that interesting? And in fact, I will normally go into my outputs and put a $ here so that I don't get confused about what I'm looking at. The default output system in HLA for a register is hex. We're going to do that. You cannot force binary, but you can force decimal, and we're going to do that. Okay, so now I'm going to look at AX. And since AX is covering this whole thing, that should be 00 FF. So there's AX. So remember, 1 digit of hex becomes 4 bits of binary. So 8 bits is 2 nibbles or 2 hex digits. AH is 8 bits, so 2 hex digits. AX is 4 nibbles or 16 bits, so 4 nibbles is 4 hex digits. And if I do EAX, finally, I'm adding the $ to my output because I think that makes it easier. I'm going to line these up too because I think it'll look nice. I added the $ because HLA does not print the $. So I'm added the $ so I would know for certain that I'm looking at a hexadecimal value. So EAX is going to be all of these. 0, 0, 0, 0, 0, 0, FF will be EAX's contents. So the point there is in part to just kind of get you accustomed to the idea that if I change the bits in AL, I am also by extension changing the bits in AX, and I am also by extension changing the bits in EAX. All right, so how do you make these things look like binary? So, decimal. So the question is asked, can I force it to output in binary? And HLA does not have that built in, but we are going to create a function for ourselves to do that in a few weeks, where we can get it to print out binary sort of manually. But you can force HLA to print in decimal. So hopefully everyone's taken that. If I do an output with the register, by default I get hex. And it's a good idea to add a $sign to your outputs so that when you're seeing the value on the screen, you're not confused about whether or not it's hex or decimal. So if I want to force the issue, I do this. So I'm going to take the $sign out because this is going to be decimal. You do a typecast. In HLA, it looks like this. We're going to typecast to be uns 8 for AL. So this is an unsigned 8-bit integer. The sizes have to match. So AL is 8 bits, so I have to cast it to be something that's 8 bits. But what this will do is cause HLA to spit it out as a decimal formatted value. So I'll run that and we can look at it. I'm going to put an extra new line in here. You can do that in HLA, by the way. There's a function just to put out a blank line, which I use quite a bit. So there it is, the AL, but now I've forced HLA with the typecasting operation to spit it out in decimal format. So that's how you can get a register to look like decimal. I'm not going to do AH because it doesn't have anything interesting in it, but I am going to do AX in decimal. So this time, we have to think, what can I cast it to here that's the right size? You're correct, Captain Price. UNS 32 for that. So correct. Good one. UNS 16, so AX is 16 bits of register. So something that's 16 bits to cast it into. So it'll look like decimal. And let's go ahead and use Captain Price's solution for the last part, which is EAX in decimal is, I'm going to line these up. UNS 32 because EAX is 32 bits of register. And then we'll look at that. The reason why these all look like 255 because at the end of the day that's what the value is an unsigned integer. Even if we consider all of EAX, that's still all of the data is just there and the rest of it's sort of just zeroed out. Okay, so those are important for the lab. I'm going to kind of push them out of the way. The reason why I did this gigantic binary number is because I wanted to be able to sort of talk about the segments. So AL, AH right next to it, AX is all 16 of those, and then EAX is all 32 of those. So you can go poking around in here with moving the ones and zeros around and kind of see how that shows up. So the question is about registers, are they zeroed? So registers are not guaranteed to be zeroed in HLA, so if you want them to be zero, you should be careful that they are zero. Variables, on the other hand, when you declare a variable in HLA, those will be zeroed for you. Okay, so I've got a few minutes, so I can give you a couple more tips. So anyway, the question Captain Price asked, with registers, you should not assume that they are zeros to start. Now, if you immediately move data, then you know what it is. But you should not assume that they're zeros to start. And if It's important. So the question is there a difference between EAX and EBX? No. They're just two different memory cells. It's like two different variables of the same size, and they're also set up the same way. So if I wanted to, this whole example would work with the B segments just the same. So they don't work any different. They're just two variables that share the same kind of behaviors. So that's a good question. And EBX is the same. I could change this to all ECX stuff or all EDX stuff, and it would be all the same. Hopefully everyone recognizes, by the way, if this, by the way, that's a decimal 0, but HLA will pad it out as needed. If I move 0 to EAX, I am also I get it for free. I am also zeroing out AX, AH, and AL because those are all in there. So that's kind of nice. All right, so let me go pick off a little bit of the lab and see if I can be of some use to you before we run out of time on that. So let me bring up the, what do I want, the browser, which is not in the front. Okay. All right, what are we supposed to do? Document a loop, same loop that we used last week, so I'm not going to do that part. Okay, so this one's going to be fun because we are not using any variables, we're only using registers. Okay, so you are going to need some help with this one. Oh, by the way, so that'll make sense now what I was trying to show you up here at the top. The typecasting to get decimal versus hexadecimal. But let's set up and do one of these sections. So let's see. I'm going to do the middle one. So I'm going to read in 4 and 16, and then I'm going to show the X's and then the L's. Apparently it didn't ask me to do the H's. You can actually, C++ will actually let you intermix actual assembly language anyway, so if you wanted to directly manipulate registers in C++, you actually can do that. So yeah, C++ will let you get in there and muck around with the registers if you want. It has a little weird setup to do it, but you can. Okay, so we need to get some inputs. And a little bit of this is you're just going to have to take a bit of a leap of faith with me and believe me about what I'm saying. So I'm going to clear this out for now. I'm just going to save this as September 9 notes. I'm just setting aside what I did a second ago, so if I need it later, I can come back to it. But otherwise, I'm going to reopen Lab 3, and I'm going to start over. Okay, so except for it's now what's going on? I don't know what's going on. Oh yeah. Wait, do I have it open twice? I do. Okay. Close that. Okay, we're back. So I'm doing the 16-bit section, just so you know. Because I think this is the one, I mean, I can do this one and hopefully then you can sort of extrapolate to the others. So what I'm supposed to do is prompt for and read in, I believe, 4 values. So that's going to look like this. And I'm not using any variables, by the way. I'm only going to use registers. I'm going to be lazy about this. We're going to assume that only other programmers are going to use this and they'll know what I mean by a 16-bit number. And what I want is I'm going to use the standard input handling routine to get an unsigned 16-bit integer. Now this is yet another one of those things like you're just going to have to get used to this. So that is the way that I can read in an unsigned 16-bit integer from the keyboard. So I'll leave you some hints up here. You're going to use unsigned 8 bits in the top section, and you're going to use unsigned 32 bits in the bottom section. Okay, but here's the trick about this. It doesn't look like the data goes anywhere. Like, okay, so I read in a 16-bit integer, but where is it? Well, the way this routine works is that it leaves their input data sitting in a register. And it leaves it in a specific register. And I'll leave some notes behind for you that. So if you read the documentation, it will tell you that if you run this routine, it's going to deposit the keyboard input into the AX register. Now, it could have been the BX register, it could have been the CX register, it could have been the DX register. Those are all 16-bit registers, but the person who wrote this procedure in the libraries decided to use the AX register for this routine. So there's nothing we can do to change that. That just is what it is. The 16-bit part makes sense, of course, because we're trying to get a 16-bit integer. The fact that it's AX and not one of the others, that's because the designer of this routine chose AX. So when this is done, the input is left behind in AX. Now what the assignment says to do is I actually want to store the first input in DX. So immediately after that, I need to take the AX that is currently holding the keyboard input, and I need to copy it into the DX register. This is based on the instructions. So how do I know it was in AX? Because it's in the documentation. So I immediately, and move means copy, I immediately copy the keyboard input that I know is in AX into DX, and then I come back. In fact, I'm going to say enter first, second, third, and fourth. So I'm going to now do another one. You don't make the input assigned to the register. That happens automatically, but this move instruction is how I'm copying it over. I'm going to do all the examples, so that'll come. So I'm going to use this get U16 routine again because I want a 16-bit. The U means unsigned 16-bit integer. I know because of the documentation that that's going to leave the keyboard input in AX again. But for this second one, I'm going to use a move instruction, which really means copy. I'm going to use the move instruction to copy the new input that's now in AX into the CX register this time. So the first input got copied over to DX. The second input got copied over to CX. The third input also still an unsigned 16-bit because I'm still in the 16-bit section. So I know it's in AX because that's where get U16 puts it. So I'm going to use the move, which actually means copy. I don't know why they chose to call it that, but they did. The move instruction to copy the third input from AX, which is where they always go, into BX this time. Yeah, so Captain Price is pointing out that it's pretty repetitive, and that is totally by design. I wanted you to sort of have to repeat the same things over and over again with the hope that you would start to say, okay, I'm starting to get a feel for this. At least for some of you, maybe you're learners like that. Fourth 16-bit number. This one's an AX, so I'm just going to, your fingers may want to do this, but you may realize that for the last one that I actually want to just leave it in AX, I don't actually have to copy it from AX to AX. This doesn't really hurt anybody, but it's unnecessary for the last input, which I want to be in AX, so I will just leave it where the routine put it. So for the first one, I don't want it in AX, I want it in DX. The second one, I don't want it in AX, so I move it to CX. The third one, I don't want it in AX, so I moved it to BX. The last one, I want it in AX, so I just leave it there. Okay, so that's the input parts. Now what I'm supposed to do, I believe, is display the contents in hex and decimal for all of those. Thanks for your patience, by the way. I know I'm sort of gone over. So we're supposed to output all these values in hex and decimal, and I'm going to do them all as one-liners. So the first input, I have to remember that the first thing they input in the sequence was I copied it over to D. So the first input, I'm just kind of whatever I want. I know I'm going to output it in hex first. It lives in DX, comma DX. So that's going to come out as hex by default, and that's one of the requirements is that I show it in hex and in decimal. So I'm also then going to put, maybe I'll just put like a comma here. That's kind of hard to look at, but the comma space in quotes is so that that's in the output. And then the comma in the command is there to separate the parts. So first input, $, and then DX register, which is going to be the hex. And then I'm going to typecast this to be an N16 because it's a 16-bit register to show it in decimal. So this will show the first input, DX, that's where I put it. It's going to show it in hex first, followed by a comma, and then it's going to use typecasting to show it as decimal. And then I'm just going to repeat that process for all of them. And I'm going to sort of go back and line things up as I go because I think it'll look nicer that way. CX is where I copied the second one to. Put a little comma in the output, and then I will use typecasting, HLA typecasting to get the decimal view of the thing that I want. That one's in BX. And the last one, the fourth one in the sequence, is in AX still. Okay, so that's the first part of that instruction is let's just show them their outputs. I mean their inputs. So the first 16-bit one, the second 16-bit was in C. The third I copied it to B. The fourth I left it in A, and then I showed it in hexadecimal, which is the default, and decimal, which I got by typecasting. It also tells me to show the C's. And this might be where I trail off. I'm not happy with the first input, second input, but that's fine. So let's show DL. Let's see, I could technically do this for the 8-bit. That's correct, Captain Price. And that's actually better than what I did. So Captain Price in the chat is saying, like, I kind of could direct them to specific ranges of values, and that would be better than what I did to do that. So that your user, which will be you, but your user knows, like, that's what I mean here. So this was me being sort of going through it fast and being a little lazy. So the second part of the 16-bit section asks you to print out the DLs. And I just want to point out to you, the reason we're doing that is because I want to remind you that if I change DX, there's a good chance that I'm also changing DL at the same time. So the whole reason for this second part, where it will now show DL, well, what's the point of that? The point is for you, as you're learning this, those are 8 bits, to remember and sort of get it sort of pounded into your head that any change to DX probably changes DL, at least has a high chance of changing DL. So the reason why we're doing this extra bit of outputs here is so that we get this reminder on our fingertips that, oh yeah, why would I print out CL here? Oh, it's because I was just working with CX, and any change to CX may change CL, so why don't we see what that looks like? That's what this part's about. I hope that made sense. CL. And also just to give you more repetition on the typecasting. So remember, DL is the lower 8 bits of DX, and DX contains the data from their first keyboard input in this section. So BL contains, and again though, this is really just because I hope that some people find it useful to sort of understanding what's going on here. A change to DX may change DL because they are the same thing, right? Just DL is a certain portion of it. A change to CX may change CL, same reason. Change to BX, BL, and then finally a change to AX has a good chance of changing AL as well. Also, you get a lot more of practice with just sort of muscle memory in HLA. So that's those things. Did I do anything that might not compile? I'm going to go ahead and see if it compiles before I leave off here. So you'll notice, I'm going to come back and compile in a second. Let me re-enable the browser. So I have done this section here where I have read in 4 un16s and I stored them in DX first, CX second, BX third, AX fourth. Then I displayed the contents of those registers, which is where their 4 inputs have been stored in hexadecimal and decimal formats. And then I also displayed the contents of these lower 8-bit segments, just to try to call your attention to the fact that changes to these 16-bit segments have a very good chance of making changes to these 8-bit segments that are underneath them. So the last section, and I'll go back up to the first one, the last section has you repeat the whole process, but this time on 32-bit inputs, and then show the 32-bit registers in both formats. And then as a reminder to you that changes to the 32-bit segments will change the 16-bit segments, I have you do those outputs, which also changes the 8-bit segments, so I have you show those outputs. That's why that's all there. The least painful section is the 8-bit section, because if you store something in the L's, that's the most interesting thing about them. Yes, so you will wrap your whole program in a for loop so that it can be run. Like, would you like to enter a whole bunch of numbers again? Yeah, ask your user that, just like you did on the second week's lab. Bring that same for loop over where you ask your user, would you like to do all that stuff again? Yes. I think that's in here. Yeah, so the second requirement is that you have a loop to repeat. I never did compile. Let's just end the show on me compiling, and please don't make a mistake. Okay. 3. All right, so it's going to ask me for numbers. I'm just going to go like 50, 100, 150, 200. So there it's showing me the 16-bit segments. And then the idea here is that when you look at the output of your program, you're like, oh, wait, where did that 32? Oh, that's the same 32 that I'm seeing up here in the DX, because this is really part of DX. So it ought to have the 32 in it. Just like CX, the CL ought to have 64. That's hex, by the way, obviously, because these were my actual inputs, and so on. So you're going to have a whole bunch of this stuff repeated for the different sizes of things. but I just did the middle section, so you can always grab it out of the video if you want. Hopefully, by the way, the calculator trick helped. On your Windows system, your calculator has a programmer mode that will do some of this stuff, but I like this one better actually. If you're on a Mac, the calculator will also do programmer mode and let you do all these manipulations. If you're already on a Linux, my Ubuntu has a different calculator than this, but it has the same kind of setup. Okay, it's 12:15. Thanks for hanging around for the extra 15 minutes if you're able to do so. I'm going to call it a day there. I'll post this video later today after I get it moved around for captioning and stuff. And otherwise, I hope all of you have a good afternoon, the best afternoon, and the best rest of your week that you can have. Canvas inbox me if you have questions. Drop questions into the Piazza discussion. It's great to get those things going. And good luck.